Hi everyone, this is Amarnath. Welcome to my video lecture, MLR Institute of Technology, Hyderabad. Today my subject linear algebra and calculus, continuous lecture, continues to the eigenvalues and eigenvectors topic. La previous lecture we discussed about how to find eigenvalues and eigenvectors of a 3x3 matrix, 2x2 matrix, when eigenvalues repeated and distinct. All cases we have discussed very clearly, and alternate methods also we discussed. Now in the present lecture, applications of this eigenvalues and eigenvector, that is Cayley-Hamilton theorem, one of the important theorem. This verification we will do, and some applications of the Cayley-Hamilton theorem we discuss. So what is the statement of Cayley-Hamilton theorem? So according to the Cayley-Hamilton theorem, every square matrix satisfies its own characteristic equation. This is a statement of the Cayley-Hamilton theorem. Every square matrix, any square matrix, 2 by 2, 3 by 3, 4 by 4, it will satisfy its own characteristic equation. At every square matrix we can define a characteristic equation. So what do you mean that one? That we will discuss. So sometimes there in the examination they are asking very clearly, write the statement of Cayley-Hamilton theorem. So every square matrix satisfies its own characteristic equation is a statement of the Cayley-Hamilton theorem. Let us take one n cross n matrix. Let A be the n cross n square matrix. Then what is the characteristic equation of the square matrix? We know the very well, that is det of A minus lambda I is equal to 0. Since it is a n cross n matrix, we will get highest power of lambda is lambda power n. So let us expand in general terms. I am writing highest term will be lambda power n. Then automatically the powers will be decreasing, lambda power n minus 1, lambda power n minus 2, lambda power n minus 3, so on. So lambda power n minus 1, then coefficients, small coefficients will be there, depends on the matrix values, that I am writing A1 lambda power n minus 1. So alternate signs will be generated, that will be given by minus 1 whole power n, that I am writing whole into plus lambda power n minus 1, and A2 into lambda power n minus 2, slowly lambda powers are decreasing term by term, A3 lambda power n minus 3 plus and so on, plus last coefficient constant term. So in every equation already we have seen so many problems we have done, their characteristic equation end with the constant. So an, which is equal to 0. This is a general characteristic equation for n cross n square matrix. So these A1, A2, A3 are the coefficients that will be changing term to term, depends on the given matrix, that coefficients to be determined. This is the general equation for characteristic equation. Now what the statement says, square matrix will satisfy, what is the square matrix we have taken? A, that will satisfy this equation, means the lambda will be replaced by A, that is called Cayley-Hamilton theorem statement. So since according to the Cayley-Hamilton theorem, according to Cayley-Hamilton theorem, square matrix A will satisfy the above equation, nothing but lambda will be replaced by A. So briefly I am writing, that is the meaning of satisfying, means we can replace lambda with the A, minus 1 whole power n into lambda power n. So lambda power n, lambda will be replaced by A, that is A power n plus A1 into capital A power n minus 1 plus A2 into A power n minus 2. Everywhere wherever the lambda is there I am replacing A, plus A3 lambda power n minus 3 plus and so on, plus, so in the place of lambda we need to replace lambda A, and the last one is a constant term, that is a constant. These all are matrices, it cannot be a constant, that should be multiplied by I, because since these all are matrices, some constant cannot be added. So that will be, remember, constant will be multiplied by identity matrix of the same order, 2 by 2, 2 by 2 identity matrix, 3 by 3, 3 by 3 identity matrix is equal to 0. Exactly I replace the lambda with A, that is the meaning of Cayley-Hamilton theorem statement. So it is a polynomial in A, powers of A, x square, A cube, A power 4, A power 5, like that we get the polynomial in A, and the constant will be multiplied by I of the same order. Now, so this is a meaning of the Cayley-Hamilton theorem, means if you find all the powers of A and adding, the finally you will get a null matrix, 0 matrix. That is called verification of the Cayley-Hamilton theorem. Suppose he is asking verify Cayley-Hamilton theorem means we need to find the character equation, replace lambda with A, and adding all the matrices you will get a null matrix. Each element of the matrix will be 0. That is a called null matrix. That is the verification of the Cayley-Hamilton theorem. So, example, let us say suppose we have taken a matrix of 3 cross 3. Let us say we got a one characteristic equation. Let us say we got lambda cube minus 3 lambda square plus 6 lambda minus 7 is equal to 0. We got one chaotic equation. Now, according to Cayley-Hamilton theorem, this A will satisfy this equation, means what the equation becomes, lambda will be replaced by A, that is A cube minus 3A square plus 6A, and since 7 is a constant, it will be multiplied by identity matrix 7I. So, this will become like this for any given matrix. Suppose example, just I have written one simple equation where it is in the lambda, that will be replaced by A. Now, take A cube, A square, A and 7I. Yeah, if you add all these matrices, you will get 0. That is a Cayley-Hamilton theorem statement verification. Let us do this verification and applications of the Cayley-Hamilton theorem now. So, here we have small applications of the Cayley-Hamilton theorem, that is we can find the inverse of a matrix for any given square matrix. We can find the inverse, such as A inverse we can find, A power minus 2 we can find, inverses we can find using Cayley-Hamilton theorem. And to find higher powers of a matrix, higher powers of a matrix means, so A power 4, A power 5, A power 6, the A power 8. So, like the higher powers we can find. The two applications especially here, important applications, and other than that, this also we have expressing a in linear polynomial given matrix, that also we have. So, these two first we discuss how to find inverses and how to find the higher powers of a matrix using Cayley-Hamilton theorem statement, right. Now, let us explain with this problem. Now, let us take one small problem here. I am taking a 3 cross 3 matrix and asking verify Cayley-Hamilton theorem for the matrix, it is a square matrix, and find A inverse using the Cayley-Hamilton theorem. So, for this one what we required? Characteristic equation. Let us start the problem. So, to apply the Cayley-Hamilton theorem, we need to find characteristic equation. The characteristic equation of A is det of A minus lambda I is equal to 0. We know very well in the eigenvalues, eigenvectors topic, we have discussed very clearly how to find this one, and that is a det of, from the diagonal subtract the lambda, from the diagonal element subtract the lambda, 2 minus lambda 1 2, remaining will be no change, 5 diagonal element 3 minus lambda 3 minus 1 0, third diagonal element minus 2 minus lambda. So, this is the only subtract from diagonal element minus 2 minus lambda, which is equal to 0. Okay. This is the chaotic equation, and generally we can do this one in two methods. We have discussed very clearly two methods, expanding determinant. Another one is a shortcut method, that is formula based, that is lambda cube minus S1 lambda square plus S2 lambda minus S3 is equal to 0, where we need to find S1, S2, S3 values. If you do not know the formula, you can expand generally how we expand the determinant, where S1 is equal to trace of the matrix. So, already we know this one how to find. So, again I am explaining, S1 is trace of the matrix, sum of the principal diagonal elements, 2 plus 3 minus 2, which is equal to 3, to this principal diagonal element sum of, right, but that is S1 is 3, S1 is equal to 3. Next, S2 is equal to, this is the sum of the cofactor matrix of principal diagonal elements, that is 2 minus 3 minus 2, for this one cofactor matrix, after leaving that row and column and the det of the remaining elements. First element 2, leave that column and row, remaining 4 elements 3, 3, 0, minus 2. So, first that is determinant is 3, 3, 0, minus 2, det. Next, plus second diagonal element 3, leave that row and column, at middle row and middle column and remaining 4 elements, the corner elements 2, 2, minus 1, minus 2. Next, last element minus 2. So, for that one, leave this last row and last column, remaining 4 elements 2, 1, 5, 3. So, this that will be give the S2. So 3 into minus 2 minus 6, 0 into 3 0, plus now 2 into minus 2 minus 4. Next, minus 1 into 2 minus 2, minus of minus plus 2, plus 5, 2 into 3 6, 6 minus 5. Okay. So, here plus 6 minus 6, right. So, what is the leftover here terms? Minus 4 minus 5 minus 9 plus 2 minus 7, that is a S2 value minus 7. These are the values of S1, S2. S2 is equal to minus 7. S2 is equal to minus 7. Next, let us find S3. What do you mean by S3? Det of A. S1 is trace, S2 is principal diagonal elements cofactor matrices value, S3 is the determinant of A. So, determinant of A we know very well how to find. So, first row I am expanding 2 into, so 3 into minus 2 minus 6 and minus 0, minus 1 into second element, first row I am expanding minus 1, the first row first element plus minus plus, leaving the middle row and first column 5 into minus 2 minus 10, minus 1 into 3 minus 3, last element 2 into, so 5 into 0 0, minus 1 into 3 minus 3, minus of minus plus 3. So, which is how much? 2 into minus 6 minus 12, minus 10 minus 3 minus 13, that is into minus 1 plus 13. So, 2 into 3 6. So, 13 plus 6 19, 19 minus 12, this is a S3 is, so that is minus 12 minus 10, second element minus 1 into 5 into minus 2 minus 10, minus 1 into 3 minus 3, minus of minus, this is plus 3, minus 10 plus 3, that is a minus 7, minus 7, a small minus 7, minus of minus plus 7, right. So, 7 plus 6 13, 13 minus 2, so that is a minus 12 and the value is 1. Okay. S1, S2, S3, substitute in equation 1, that is the required chaotic equation, substitute in equation 1. That's what you are getting, that is, so I will write in the next page. So, S1, S2, S3, lambda cube minus S1 lambda square, 3 lambda square plus S2 lambda, S2 means here minus 7. So, minus 7 lambda minus S3, S3 value is 1. So, the equation is lambda subcube minus 3 lambda square minus 7 lambda minus 1 is equal to 0. This is a characteristic equation. So, let us apply the Cayley-Hamilton theorem in the next slide. So, what we got the characteristic equation? Lambda cube from the previous equation, lambda cube minus 3 lambda square minus 7 lambda minus 1 is equal to 0. So, this is the previous characteristic equation, lambda cube minus 3 lambda square minus 7 lambda minus 1 is equal to 0, right. This is the equation. Now, according to Cayley-Hamilton theorem, a matrix A, square matrix A will satisfy this equation. So, according to Cayley-Hamilton theorem, Cayley-Hamilton theorem, A will satisfy, matrix A satisfies above equation, satisfies above characteristic equation. What is the equation? That is nothing but lambda will be, to make you understand I am writing, lambda will be replaced by A exactly. So, A cube minus 3A square minus 7A, the minus 1 is a constant. So, since these all the matrices constant cannot be added to the matrices. So, that is why it is multiplied by I, the 1 into I, that is equal to I, that is equal to I am writing I is equal to 0, which of the same order. So, this is the main polynomial in A according to Cayley-Hamilton theorem. Now, since he is asking to verify the Cayley-Hamilton theorem, find A cube value, A square value and A, and adding all you have to get the null matrices, right. Let us write first A square value. A square value is A into A, multiplying A. So, that when usually we can find with the calculator, right? That I am writing the a square value directly. What is the a square value? Here I am determined value, predetermined value 7, 5, 3, 22, 14. The students know very well how to find the a square. 0, minus 1, 2. Next, a cube value, that is a square into a or a into a into a, that is 36. This is also predetermined value I am writing. In the scientific calculator easily we can find powers of a matrix. Just enter in mat A and mat A into mat A into mat A 3 times. If you multiply, you will get a cube in the scientific calculator, right? A cube value. Now substituting all these values in the above equation to, we can verify it is a null matrix or not, because we need a square and a cube, and a is a given value, I is the identity matrix of 3 by 3. Let us write the equation: a cube minus 3a square minus 7a minus I, which is equal to, right, I am writing a cube. So which we have here 36, 22, 23, 101, 64, 60, minus 7, minus 3, minus 7, minus 3a square. We have a square value which is predetermined, 7, 5, 3, 22, 14, 13, 0, minus 1, 2, right? Minus 3a square minus 7a, 7a, a means given matrix. So given matrix, let us have the given matrix, that is 2, 1, 2, 5, 3, 3, minus 1, 0, minus 2, right? Next, minus I, identity matrix. Identity matrix means minus I means identity matrix of 3 by 3. We know very well 1, 0, 0, 0, 1, 0, 0, 0, 1. This is the identity matrix of 3 by 3. See how to add these all elements means we need to add the corresponding element. So I will add and show you one corresponding element. First element 36, right? So here second element minus 3 into 7, minus 21, minus 7 into 2, minus 14, minus 1. This is the first element. Next second element 22, right? Next minus 3 into 5, minus 15, minus 7 into 1, minus 7. The last element is 0, right? So similarly third element 23, here I am separating this one, right? Now third element 23, minus 3 into 3, minus 9, minus 7 into 2, minus 14, and the last element is 0. Now let us check these values simply. Here I am not evaluating all, so you will understand. So 36 minus 21 minus 14 minus 35 minus 36 plus 36 minus 36, 0. Second element 22 minus 15 minus 17, 0. Next 23 minus 14 minus 9, 0. See very clearly we are getting all values are null values, that is 0. So you can check the remaining elements 1, 0, 1, minus 3 into 2, 22, minus 66, minus 7 into 5, minus 35. So 101, 101, 0. Next second row second element 64, minus 3 into 14, 28, 32, 42, minus 7 into 3, 20. So which is second element, minus 3 into 14, 28, 32, 42, minus 7 into 3, 21. So that is 42, 23 into 14, 42 and 21. So these all elements we can clearly we can say these all elements are going to become 0, right? So we can add all elements, that is simply we can write 0, 0, 0, right? I am not evaluating all, that's we can do that remaining evaluation part. So this is clearly we got 0, means the equation is satisfied, the above equation is 0, null matrix, it is a 0 by 3, 3 by 3 null matrix. So clearly we have shown this value a cube minus 3a square minus 7a minus I is equal to 0. So what you can conclude, therefore Cayley-Hamilton theorem is verified. Cayley-Hamilton theorem is verified. For what? For given matrix A. So this is a Cayley-Hamilton verification, and is asking to find A inverse. Then how to find the A inverse using Cayley-Hamilton theorem. So, this is the main equation is 2. From these two equation, whatever applications he is asking, we can do. So, what is the equation? A cube minus 3a square minus 7a minus I, which we have using Cayley-Hamilton theorem. So, right. So, to find A inverse, for the given matrix using A inverse we can find in many ways, but he is asking use the Cayley-Hamilton theorem, that application of the Cayley-Hamilton theorem. That is right. We have in earlier, we have in the next slide what we have the previous slide, Cayley-Hamilton theorem. As per Cayley-Hamilton theorem, we have the equation a cube minus 3a square minus 7a minus I is equal to 0, which we derived in the last one. Look at this one, same equation, a cube minus 3a square minus 7a minus I is equal to 0, that I am going to use to find the A inverse. Very simple. To find A inverse, multiply by A inverse on both sides, that is A inverse into a cube minus 3a square minus 7a minus I is equal to 0, right. So, we know very well how to multiply matrices A inverse into a cube at a power 3 minus 1, that is a square minus a square into 3 as it is, a square into A inverse, a powers base are equal, power should be added, 2 minus 1, 1 minus 7 into A inverse. We have any matrix when it is multiplied with inverse, the result is identity matrix, that is 7I, right. Next, A inverse into I, that is A inverse. Why? Because any I into A inverse, again A inverse only. We know I is the identity elements. When you multiply any matrix, we get the same matrix, A inverse. So, which is equal to 0. Right side, A inverse into 0, 0. So, from this one, what I want? A inverse I want, right. A inverse is equal, take the other two other side, that is A square minus 3A minus 7I. Okay, this is a inverse. So, then do we easily can find A inverse, because we have A square, A value, identity value. So, we can find A inverse is equal to A square. In the previous problem, we have done A square value. That A square I am taking 7, 5, 3 predetermined value 22, 14, 13, 0, minus 1, 2. Minus 3A, A means given matrix. What is the given matrix here? 2, 1, 2. Next 5, 3, 3, next minus 1, 0, minus 2, minus 7I, I means identity matrix of 3 by 3, 1, 0, 0, 0, 1, 0, 0, 0, 1. How to add all the elements? We know very well all corresponding elements. Just now we have done the previous problem, 7, minus 3 into 2, minus 6, right, minus 7 into 1, minus 7, first element, second element, 5, minus 3 into 1, minus 3, minus 7 into 0, minus 0. Next, third element, 3, minus 3 into 2, minus 6, minus 7 into 0, 0. Second row, 22, minus 3 into 5, minus 15, minus 7 into 0, 0. Next, second element, 14. Here second element, 3 into 3, 9. Next, minus 7 into 0. Minus 7 into 1, sorry, minus 7, last element, 13, second row, last element, 13, minus 3 into 3, minus 9, minus 7 into 0, 0. So, third row, first element, 0, minus of minus, plus 3, minus 7 into 0, 0. Second element, minus 1, minus 3 into 0, 0, minus 7 into 0, 0. Third row, third element, last element, 2, minus 3 into minus 2, plus 6, minus 7 into 1, minus 7, right. These are the values. So, simplifying, so easily we can get the values, that is 7, minus 7 plus 7 gets cancelled, minus 6, 5 minus 3, 2, 3 minus 6, minus 3, 22 minus 15, 7, 14 minus 16, that is minus 2, 13 minus 9, 4, 3, minus 1, 2 plus 6, 8, 8 minus 7, which is 1. This is a required A inverse, right. Similarly, we can find higher powers also for this matrix. So, this is application. So, A inverse can be determined by many methods. So, this is one of the method using Cayley-Hamilton theorem. Generally we have A inverse is equal to 1 by det A into adjoint of A. That is the generally we do. But here I am using Cayley-Hamilton theorem to find A inverse. Similarly, you can find A power minus 2 multiplied by A power minus 2. You can find A power minus 2 multiplied by A power minus 3. You can find A power minus 3. Further, we can find any inverses using this Cayley-Hamilton theorem. Suppose he is asking any powers of a matrix and to find A power n using Cayley-Hamilton theorem. So to find this one, again we use the same equation which we have done. Suppose he is asking to find A power 4. To find A power 4. So what is the equation we have using Cayley-Hamilton theorem? That is A cube, basic equation, 3a square minus 7a minus I is equal to 0. This is the basic equation. Now I want A power 4 multiply by, you can expect here already we have A cube, you want to get A power 4, just multiply by A on both sides of the equation. So what is the A cube into A power 4, directly I am writing A square into A cube minus 7 A into A square minus I into A is equal to 0, right. Now I want A power 4, make it as a subject, remaining transport to other side, 3A cube minus 7A square. So minus take to other side, plus minus will become as a plus 7A square minus A becomes plus A. So A power 4 as a subject. So this is a cube, already we have A square, we have A, we have, adding all these we get A power 4. Suppose he is asking to find A power 5, multiply by A square on both sides. So you will get highest is A power 5. A power 6 multiply by A cube, the above equation, you will get A power 6. Like that we can find the higher powers of a matrix. Since we have all these values, if you add you will get the required higher power of the matrix without finding actual, without doing actual multiplication. This is called application of the Cayley-Hamilton theorem. So in this clearly we have understood how to find the inverse and how to find the powers, right. Here I am giving some problem for practice. So verify Cayley-Hamilton theorem, hence find A inverse, and here that is one more 7 2 minus 2 6 minus 6 minus 1 2 6 2 minus 1. Right. In this session, clearly we have discussed what is Cayley-Hamilton theorem and its applications. And in the next class, we are going to discuss about some more application, other applications expressing as a polynomial term and problems related to that we will discuss. Right. So this is my lecture. Thank you. One and all.